Hi everyone and welcome back. It's Kira Garfolo with Greenville Tech's Math 109. Today we're going to talk about section 3.3, which is power and root functions. So first we're going to discuss power functions. And power functions are functions that can be written in the form of y equals ax to the b, where b is not equal to 0. Remember, if we have an exponent of 0, it makes that whole term, like that x to the 0 would be 1, so we would have a constant, and it would kind of defeat the whole purpose of this discussion. So you're raising something to a power. You've actually already seen some of these, you just didn't call them power functions. What we've already seen in quadratic functions is an example, y equals x squared, right? We have y equals, in this case, a is 1 and b is 2. There are lots of special power functions that we're going to see throughout our course. And some of them, that we're going to have to become familiar with. And don't worry, you don't have to memorize these right now. You're going to become familiar with them as you go. I would encourage you to take a look in your textbook at these, as you'll get much clearer pictures. But you get the idea here from the image here. So what we're going to call these a lot of times are parent functions. And we'll revisit them throughout the course, especially when we start talking in chapter 4, where we're doing transformations. We're going to start with these basic power functions or these basic parent functions, and we're going to move them around. A lot of times when we talk about functions, especially power functions, we're going to talk about something called concavity. And basically that means we're going to describe something as concave up or concave down. And if we say that a graph is concave up, it means that the function is increasing at a rate slower than y equals x. So remember that we have y equals x here as this line. And if it's increasing slower than that, it's going to dip below it and increase up there, okay? So that's going to be concave up. If you want to think about it, it's going to think about your graph opening upwards. If you have a parabola, it's going to be opening upwards like a cup, okay? Concave down, on the other hand, we still have that y equals x line, but now we're going to say that the function is increasing faster, so it's going to go above it, okay? If you want to think about a parabola still, you're going to have it opening downwards. Okay, so just think about where it opens, if it's opening upwards or if it's opening downwards. There are much better ways to tell this as far as the increasing and decreasing rates. And if you are going on to calculus, you will see this in a kind of really simple way to do this in calculus. So in photos, we can see the concavity. Like I said, think about where it is opening. When you have half of a graph, I find it helpful to say, okay, well, if I continued that graph, what would it look like? Or if I mirrored it, what would it look like? Am I opening upwards or am I opening downwards? You can see some other great resources at this link below to include this picture that I included. Now, sometimes you want to look at concavity pre-calculus, right? We haven't hit the calculus side in our course, but we can easily tell if it's concave up or concave down a lot of times looking at a power function, okay? If we have y equals a times x to the b, as long as our a is greater than 0, okay, so we have a positive version here. We're not flipping anything around like we'll see in chapter 4. As long as this is positive, then if b is greater than 1, you're going to have that concave up. And if b is less than 1, you're going to have concave down. So think about, square root function. You have to the half power here. You have to the squared power here, things like that. Now, negative exponents come into play a lot of times in power functions, okay? Negative exponents don't have to be as tricky as they sometimes look to students. All that means is that we're moving it to the bottom. So x to the negative 4 would be 1 over x to the 4. If I have x to the negative 2, then it's going to be 1 over x squared, okay? It's just going to turn it over to the bottom. Now keep in mind here that we cannot divide by 0. So here x cannot equal 0, okay? So x equals 0 is not in the domain because we would be dividing by 0 and we would have a problem. A special case of negative exponents is what we call the reciprocal function, which is x to the negative 1. So we're going to take x to the negative 1 power, which basically just puts 1 over x, which, as many of you will recall from a previous class, 1 over x is the reciprocal of x. Now, when we're working, especially with negative powers here, we're going to see more of these in chapter 6 when we talk about rational functions. But our domain restriction with that 0 can cause some really fun and interesting things to happen with our graph. What often counts is an asymptote. So we can have vertical asymptotes and horizontal asymptotes. We can actually also have slant asymptotes that we'll talk about in chapter 6, but not today. So a vertical asymptote is just a vertical line. So remember, straight up and down line, y equals something that the graph approaches, but it never touches and never crosses. So it kind of hugs up against and then it slides up against it all the way to infinity or negative infinity. And it's never going to touch or cross it. A horizontal asymptote, on the other hand, is the same idea, but it's a horizontal line. So now you have a y or an x equals line. I have those backwards. My apologies. I will fix them in the notes. So vertical asymptote is an x equals line, and a horizontal asymptote is a y equals line. So vertical asymptote, you'd have this here, and maybe it's this line right here. And horizontal asymptote, maybe you'd have this line right here. So you could have something come up and hug right against it, or something come this way and hug right against it on its way down. We're going to see some examples much better here in a moment. So right here, this is a vertical asymptote. This is a horizontal asymptote. Okay, vertical, horizontal. Okay, so sometimes our power function is going to have a non-integer power. Okay, so instead of y equals x squared, maybe we have y equals x to the 1/2. That's actually the square root function. If our power is rational, so that means that our power is some sort of fraction, then we have what is called a root function. And a root function, according to our text, is this fun definition, but remember, instead of y, we had our power function as y equals ax to the b, but actually now we're letting b be a fraction. And we can actually write this with radicals, okay? If we have y equals ax to the 1/n, that is the same thing as leaving that a alone, and then that 1/n power becomes the nth root. So the nth root is 1/n power. The square root, like I said, is x to the 1/2. So technically speaking, when we write the square root of x, we're talking about that 2 there. Since it's the most common one that we see mathematically, we don't usually write the 2. It's mathematically incorrect, but we don't usually see the 2 there. So some features of root functions, they all look very much the same unless we start adding and subtracting things, okay? So if we just have the pure version of the nth root of something, they all look very similar. They're just separately scaled. It does matter if our root or that value of n is positive or negative. If it is positive, then everything will have to be positive, okay? We cannot have negative x's in our domain. Our domain is all positive x's to include 0. Now, when it's an odd root, we can go across that domain. So the domain is negative infinity to infinity here, okay? So this isn't going to go below 0 on x or y, and this one's going to be all values x and y. Think about that if you have a hard time thinking about why that domain restriction counts. Think about, you can't take a square root of a negative number, right? At least not in the real number system. If you square a negative number or take it to the 4th power or 6th power or 8th power or any of the even powers, it's going to be a positive number. That's where that's coming from. Now that we have the basic understanding of power and root equations, we can talk about how to solve them. As always, you want to isolate your x term. Now, sometimes you're going to have to isolate your power term, not necessarily just the x, because it'll be tied to a power with something else, and we'll see that in our second example. Our power functions, we want to take the nth root of both sides. So that's basically saying, hey, how do you undo x cubed? Well, you take the 3rd root of it. If you have an even value of n, so you're taking a square root, a 4th root, a 6th root, and so on, you must take the positive and the negative version of that root. Because remember, if we square it or raise it to the 4th or any other even power, it's going to turn it positive. So we have to, when we're finding the original value, we always have to take the plus and the minus. For root functions, we're going to raise both sides to the nth power. So how do we get rid of a fraction power? Well, we raise it to the whole number reciprocal, right? One very important thing about root functions is that you have to check your answers. It's a good idea to check your answers anyway in all of these, but certainly check your answers for root functions, because sometimes we are going to get what we call extraneous solutions. And that means that you're going to get an answer that came out mathematically, but it doesn't actually satisfy the original statement, okay? So you need to be sure you check your answer for any answers that are given mathematically that are not actually correct. Let's work some practices here. Let's do this first one together. We start with 540 equals 5 times x cubed. So the first thing we do is get that x cubed by itself. It's multiplied by 5, so let's divide both sides by 5. That'll allow us to isolate, that x term. So now we have 108 equals x cubed. Now we want to undo raising something to the third power. So that means that we want to take the cube root of it. Okay? When we take the cube root of 108, we are going to get the answer, which if you want to leave it, this is mathematically okay. This is simplified because 27 is going to be 3 to the third. And so you can simplify it into its final term of 3 to the third root of 4, 3 times the third root of 4. Now, just as a note for those of you that are using calculators, if you need to do the third root or the fourth root or fifth root or 100th root in your calculator, I find some of them have options. I find that it's easiest to do, let's say, the fourth root of x as I just put x in parentheses and raise it to the 1/4. Okay, so you would type x caret 1/4. Okay, that's what you would be doing, or in this case to the 1/3. Just keep that in mind. Now I want you to stop for a moment and I want you to solve this one. Pause the video, do what you need to do. The first thing we're going to do is isolate that term. Notice that we can't fully isolate x on its own because it's tied to this fourth root. So that's as close as we can get to isolate, but we can certainly divide out that 4. Now we need to take the fourth root of both sides, but be careful here. Fourth root is even, right? 4 is an even number. That does not look like a V. 4 is an even number, so we have to take the plus and the minus fourth root of both sides. So we really only need to do it over here because if we do it on both sides, they'll just, as long as we have a plus and a minus as our solution. So now we're left with 2x minus 3 equals plus and minus the fourth root of 625. Well, remember that 625 fourth root is just 625 to the 1/4 in your calculator, and that's going to give you 5. So now we have 2x minus 3 is plus or minus 5. Since you have the plus version and the minus version, you now need to just use basic algebra to solve for x in both cases. So solve for when it equals 5 and solve for when it equals -5. Doing that, you're going to get the x equals 4, and then you're also going to get the x equals -1. So those are your solutions there. Let's do an example for the root function, and then I'll let you do the second example. Let's start with 3 times the cube root of x equals 12. As always, the first thing that we need to do is isolate that x term so we can divide off this 3 to get the cube root of x equals 4. Now what we need to do is raise everything. We're taking the cube root, so we need to raise everything to the third power to get our answer. So that's going to tell us that x equals 64. Now remember, it's always good to go back and check our answer. When we go back and check our answer, we get that 3 times the cube root of 64 is indeed 12. Remember, in your calculator, you could type 3 times 64 to the 1/3, and that'll still give you 12. Okay? Now take a moment and pause and work out this example. Okay, so as always, we want to divide off that 5 first. So we're going to get the fourth root of x is going to be 3, because -3, because we're dividing this by 5. Okay. We're going to raise it to the 4th power. So we're going to have -3 to the 4th power here, which raising it to the 4th power is going to give us 81. Okay. Because remember, a negative raised to an even power is going to give us a positive. So we got rid of that negative there already. Now we can check our solution. If we let x equals 81 and we type in our calculator 5 times 81 to the 1/4, that is going to give us 15. 15 is not the same as -15. So that is not our solution. So this is not a viable solution. In fact, there's no solution to this equation. You could actually go and look, you could graph this and see that it's not going to cross x at any point. Okay. So always check, especially, I mean, you should always check anyways, right? But especially if you see that even root, you're certainly going to want to check and make sure that you don't have an extraneous answer, because these negatives get kind of screwed up regularly. Okay. Now we can apply these concepts that we've just learned. We can talk about direct variation and we can talk about inverse variation. So our first scenario, we have direct variation. In direct variation, we talk about as the nth power of x. So if we say something is directly related, that's what we're dealing with here. We have y equals k times x to the n for some number k. And specifically, k is what we're going to call our constant of variation. And we often have to solve for that. Let's talk about an example. Let's say that the weight of a ball varies directly as the cube of its radius. Okay, so there's our power right there. We know that a ball weighing 380 grams has a radius of 2 centimeters. What's the weight of a ball with a radius of 5 centimeters? There's a lot of information there. What we need to do is set up our y equals k times x to the n first and solve for k. Using what we know, okay, this is going to be y and this is going to be x, okay, because we're looking for the weight of a ball, right? The weight of a ball, y, varies directly as the cube of its radius. If we want to know the weight of the ball with this radius, that means we need to write y equals k times x to the n first. Once we get that function sorted out, then we can plug in 5 and solve. So this is kind of a two-step problem. So the word cube tells us that we know y equals k times x cubed somehow. But now we need to solve for k. We know that when x is 2, y is 380. So let's plug those in and solve for k. 380 equals k times 2 to the 3rd. Okay. And so we can solve for k just simply solving that out. 380 is going to equal 8k, which means k is going to be 47.5. So now we can write our equation. Y equals 47.5 times x cubed. In this case, k is our constant of a coefficient of variation, and it's 47.5. Now that we have this, it's just a regular old function that we need to evaluate at any value of x to give us a value of y. So in our original problem, we were asked, let's see, what's the weight of a ball with a radius of 5? So now we can use this with x equals 5 to answer our original question. Plugging that in, we see that it's around 5937.5 grams. Okay. If you need to go back, pause, make sense of it, do whatever, that's fine. Now, inverse variation is very much similar. Now we're going to have y equals k over x for some value k. And it's inverse, you can think about it because x is on the bottom. Think about that reciprocal situation. Here we say that y varies inversely as x or is inversely proportional to x. You're looking for that keyword of inverse, okay? Now we can combine these things with the power and say that it's inversely proportional to the nth power. And instead of just having plain x on the bottom, now we've introduced that power of n on the bottom. We're going to do exactly the same thing as before. We're going to have to solve for k, and then we can plug things in to make predictions later. Take a moment and try this one on your own. The illumination from a light varies inversely with the square of its distance from the source. If the illumination 30 feet away is 60, what's the illumination at a distance of 20? So here we know that y is going to equal k over x squared somehow. And we also know that 60 equals k over 30 squared. So now we solve for k. And then we're going to plug that in and plug 20 into our final equation. If you're ready, here's how we do it. So 60 equals k over 30 squared. Solve for k here and you're going to get 54,000. Okay. So we know that y equals 54,000 over x squared. So for anything that we want to do, we just evaluate the function of that x. Here we wanted 20. So we plug 20 in as x, and we're going to see that our answer is 135 candela. Okay. So I know that this was a fairly heavy section, a quick section of lots of related topics. We talked about power and root functions. They're kind of the same thing. It just depends what that power is, whether it's a whole number or if it's a fraction, things like that. We talked about using those for direct and inverse variation. And apparently we've talked about inverse variation again. Practice, 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 practice here. Use all of your resources available to you. Remember your textbook. There's the departmental lecture notes. There's all kinds of things. Get the practice because you're going to need it. That's how you learn math. If you have any questions, remember that you can reach out. You can reach out to me. You can reach out on Blackboard. Math Center can help with 109. Anywhere that you need to get help, make sure that you get help and don't let yourself sink in Unit 2. Thanks for tuning in as always, and I hope to see you guys next time.